started the live stream. I've been trying to gradually put your Physics 163 videos in a playlist. I'm going to try to continue doing that. You may notice I'm a little behind sometimes and catch up on the weekend or the next week. But for the most part, almost all your videos will be in that playlist. If anybody has that playlist and wants to share it in the chat, feel free. And let's go ahead and get started with a screen share. I think we were doing this one, right? Okay, and so I think we're somewhere right around in here. Oh, that's too far. I think we were just before that. I think we were doing this. Okay, and so the last piece of the puzzle for chapter 22 is we want to deal with these continuous distributions of charge, and we're doing different shapes. Last time, we spent all of our time on rods, and hopefully you had a chance to do some of the rod problems to stay frosty on that. Now I want to talk about arcs, and the main types of questions that are going to show up on a quiz are usually going to be rods or arcs, so you're going to want to pay attention. Then I'm going to go into washers and discs, and actually some 3D stuff. And at first you may be saying, well, if it's not on the quiz, why do it? And I think what happens is when you see this pattern of learning the technique in 1D, then 2D, then 3D, I would like to think that makes the fundamentals of the techniques in 1D, which you're quizzed on, stronger. So you may be thinking, I'm not going to listen to this. I do think it's worth it to learn the 2D and 3D, just so you can start to see what's part of the pattern, what's different each time, what's not. Okay, so that said, we're looking at this piece here. We're trying to figure out doing calculus on a ring or arc shape, continuous distributions of charge. And remember, what are we really doing? All we're doing is we're saying the total electric field is the sum. Remember, an integral is like the sum of all these little point charges. So you say, okay, each point charge has a tiny amount of charge dq. That's different in every problem. Okay, and then the idea is this r vector and this r distance are going to be different at every problem. And we have to basically figure out, okay, based off the word problem you give me, what are these pieces of the puzzle? What are the limits of integration? Turn the crank. Okay. Now, if you want, you can kind of look through this really quick. Let's see if there's anything in here worth noting. Okay, we're going to, again, take an arbitrary chunk of the rod and label it. Oh, I guess here it could be an arc. I should have said arc or ring. And then we're going to write down the r vector and dq. And we need to figure out lambda if it's uniform. If it's non-uniform, lambda is given to you. And then this is something that's different. Instead of lambda dx, for arcs, we're going to get lambda ds, so arc length. And now for an arc, usually that's radius times d theta, and I'll draw some pictures in a minute. We're going to build this thing out of point charges and then turn the pieces, turn the crank. And then we make sure we pick the right limits before we do that. And then at the end, we want to check as many ways as possible. Now, I know you're probably already bored, but watch out. Remember this in general. I know it looks very similar. Read this line carefully, this common mistake. That's the most common mistake. We have to do this using the full vector. You can't use the magnitude. If you try to integrate the magnitudes, sometimes it works. Sometimes you'll be like, well, I got the right answer. It must work all the time. Ha 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 ha. Nice try. Okay, it rarely works in a few special cases. For example, a rod, when you're lined up with the rod. If everything's in one dimension, then the magnitude works because you don't have any angles. But if you have a rod in your off axis, or if you have an arc at all, so most of the time this will not work. Most of the time this does not work, but this always works. And then remember that sometimes we can use symmetry to shorten this, and that isn't listed in here. You can use symmetry to reduce the amount of work. So let's go down here and look at this one. So I'm going to look at 22.20. I'm going to start drawing it up on the board. Remember, you've got the solutions at home on the workbook or whatever. So if you want to work ahead and come up with questions, that's fine. You can throw them in the chat and I'll get to them as soon as I can and make sure there's nothing there right now. I don't see anything in there right now. Okay, good. All right. And let me get to, okay, so I'm going to draw this on the board and then I'll stop the screen share in case you're writing this down too. There we go. So the idea is, here we go. Well, I'll do that in a minute. All right. So you got a ring of charge here. Then we know we're some point up here. Okay, and the radius of this thing is R. Got it. Okay. All right, so now in this case, if you're trying to get an idea of what this might be from, I know this might seem a little bit crazy, but look at this cheesy little bucket I just found sitting here, right? Sorry, there's all these calculators from, okay, but whatever. Imagine, you can see that this is a circle, right? Imagine if I just take some fur and rub it around this top here, right? So if I just rub that with fur, we'd have a ring of charge. So you can imagine this is very easy to make in the real world. Just get a cheesy pink Easter bucket and rub it with fur. Oh man, this rabbit is probably not going to be happy about that. All right, so anyways, let's get this out of here now. Jeez. Okay, so that's what this is supposed to represent, a circle. And it's really hard to draw it and actually do the math at the same time because the angles don't show up well on a whiteboard. So I want you to think about this. Again, if I had my bucket here, we're sitting somewhere above this bucket, and I'm wondering if I rub the edge of it with fur and get uniform charge distribution, what's this? Oh, are you having trouble with the sound? Maybe I pulled the thing out. Let me restart. Whoops. Okay, how about now? Can you hear me? Wait, test it now. Now can you hear me?
You were fine before.
Oh, okay. All right. But you can still hear me now too, I guess. Sounds like it. Okay. Apologies. I don't know what it was. Okay. So in this case, it's hard to draw this very well. So let's do this. I want to get rid of this picture, even though it kind of helps us see it. And I want to focus on this one and I want to draw it a little bigger. Now, again, this is the top of that bucket. Okay. And so when we're looking at this thing, you could imagine, and actually let me make this even a little bit bigger. So when we're looking at this thing from the side, I want to look at two special points. This one, and let's do this one. Okay. At this point up here, if I put a positive charge there, and if this rod was positively charged, what would be happening? Well, if I put a plus charge here, right, I know it would be pushing away. Okay. Right? If this was positive and I put a plus charge there, it would push on it that way. Similarly, that one would be pushing this way. And so what I want to do is I could call this DE1, a small amount of electric field caused by this tiny amount of point charge. And this one I could call DE2. And maybe I wrote them backwards in the solution, but the fact remains, we could call this DE6 and we could call this DE7. It doesn't matter, right? These would be just two of the random terms here. And so the idea is we expect, by looking at the symmetry, the components, everything except for the vertical component should drop out, right? We see that this horizontal and this horizontal are in opposite directions. And now think, if we get out this Easter bucket, if we had this Easter bucket, we see that this point here and this point here, diametrically opposed, would cancel horizontally up here at this point. This point closest to you and this point way back here, they would also have that happen. And any point in this entire bucket, there's always something diametrically opposed. And we expect by symmetry, the only thing that should survive is straight up, okay? So we know in the end, the integral has straight up. So there's that piece. Now I want to draw this, well, let's think about this. What is the R vector? Well, this distance is going to be Z in the K hat. And notice in this case, oh my gosh, there's a ton of chat there. I'll check it in a minute, but sorry, I got totally distracted. I'm not trying to ignore you guys. I want to watch out in this particular problem. Notice Z is upwards. So yeah, this is going to be a polar coordinate. And oh my gosh, 26, I'm way behind. I'll catch up in a minute. But now this one, I don't want you to think of this as I hat or J hat. I want you to think of this as towards the center. So that's going to be, oh my gosh, I need some room. Again, the numbers don't matter. It's just the fact that they're different. Think about this. This is going which way? It's a circle. What's the name for going towards the center of a circle?
Inward?
Inward, true.
Radially inward?
Yep. What's the hat vector I would use? Somebody else?
Positive, oh, sorry.
Negative R hat.
Negative R hat. Let's think about that. So here in this case, it's going to go negative R hat. So positive R hat means radially outwards. Negative R hat would be inwards. And then the distance it travels, how far did I go inwards? For this problem, what was it? Was it lowercase r or capital R?
Capital R.
Okay, so the distance traveled, so I went up Z and I went inwards by capital R. And so I'm just going to use lowercase r hat here because that's the standard math way of writing it. All right, so notice, so I think I called this DE6 for no good reason. It doesn't matter. I kind of call it DE 60,228. Okay, so it's going to be K dq all over the distance squared. What's the distance? Is it Z or is it R? I'll let you think for a second. And remember, what does this mean? We're trying to figure out the electric force from a point charge. I need K, I need the amount of charge, and then I need the distance from what to what. And you don't have to answer. I'll answer in a minute. And then what's going to have to stick out there so you can get it. And I'll try and catch up on the chat. Okay, sounds like I caught up on the chat. All right, so I'm going to go ahead and say it now. From the source to the point of interest, or from the source to the point P, or from the source to the POI, however you want to say that. So in this case, the distance is not R, it's not Z, it's going to be R squared plus Z squared square root. So I'm gonna write it like this. So remember, we need some kind of vector here over the distance cubed, or you could do a unit vector over the distance squared, either one, right? So you either need to do the vector over the cubed or the unit vector over the squared. And so I kind of like doing the vector over the cubed. All right. And so in this case, the vector is going to be negative r in the r hat plus z in the k hat. And the distance, I think, is going to end up being r squared plus z squared to the 3/2. Right? And again, it's because it's square root of that, and then you have to cube it. So apologies if I'm going too fast. You've got the solutions, but yeah. Now, this is not the electric field. This is one little term. Okay. Also, we haven't figured out dq yet. Well, now remember, what are we doing? We got a charged Easter bunny bucket. Okay, so we're dealing with this bucket. The distance all the way around here. Whoops. Oh my gosh, I'm having some trouble. The distance all the way around should be 2 pi r. And the amount of charge, I think the problem said it was Q. I forgot to write it down, but I'm assuming it's just capital Q. Okay. So we know the charge density is Q over, in this case, all the way around 2 pi r. If you had an arc, this would be a different number here because you wouldn't have the whole circle. You'd have a different amount of pi r. Okay. So that's basically the difference for a uniform arc. Now, dq, whoops, I'm running out of room. By definition here, dq for an arc or a ring is going to be the charge density, the amount of charge per meter. This is, again, coulombs per meter. So I take the coulombs per meter times the number of meters I've got. Well, in this case, that's the arc length. And again, arc length should be r d theta. Okay? And there's just, I need room, so I got to erase this ds. But again, lambda is the coulombs per meter. Ds is the arc length. Remember that theta has units of radians. R has units of meters. So I have coulombs per meter times a meter times radians, which is nothing. So I get coulombs back. So I'm going to write that. And then, just so I can keep myself organized here, I might as well shove that in right now, right? So now, I'm just going to rewrite here. The r's are going to cancel. There's an r here and an r here. So I think you get q over 2 pi d theta. I'm going to double check. I think so. All right. And at this point, this looks horrible, right? Is Alexis there? Are you out there, Alexis? You might not be. Okay, maybe, I don't know if you remember, Alexis remembered seeing this the other day, and he was talking about a certain type of integral that often shows up. So when you see this square roots or 3/2, what type of integral do you normally do in a calculus class? And you can unmute if you want.
Sub.
Yeah, it looks like a trig sub, right? And so it turns out it's not. Look at this. Look at, isn't this looks so bad, and it turns out to be like the easiest integral in the class. I just want to point something out here. Q is a constant. 2 pi, constants. Capital R, that's the radius of my bucket. Is the radius of the bucket changing as you go around it? No. How about the distance above? If I was measuring the distance at this point, it's always this far up. So look at this. Constant, 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 constant. Most of that's constant. Now we got to be careful here. There's one thing in here that is dramatically changing as you go around the circle. What? Somebody other than Nick.
Theta.
theta is changing. What else? Something in here.
Oh, the R hat.
R hat. You don't notice it right away, but think about it. R hat, this time it's here and there. Crap, this is going to suck, right? Why does it not suck? Somebody other than Nick or Trey or whoever else that was that said theta. Sorry,
Symmetry.
Symmetry. How does that help us out? Which term is going to survive after we integrate?
Just the k hat, right?
Yeah, so I don't even need this term. Woohoo! Easy integral. Everything's a constant. It's just d theta. All right, so I'm going to pull this out of the way and go to the answers. You guys can go ahead and catch up. Give me just a sec. Oh, and sorry if you were putting stuff in the chat. I didn't see that till now. Okay. Where is my screen share button? All right. Oh, whoops. We need this one, I think. Is that 22.20? I think this is the one, right? Okay. And so I tried to draw this a little better in the book just because I could take my time doing it. And so you could see this is kind of what I was doing here. You could see that in this case, I actually did a J hat just in case you didn't, if you want to see this a different way. But then we know you see somewhere at some point we can ignore that. So that other term, it doesn't matter whether it's a J hat or R hat, whatever. And you could have drawn your coordinate system differently than mine, as long as you all get the final answer is that way. I don't know if you could see me hiding in the corner of the screen, wherever you are, right? We know that it's got to be upwards, and the coordinate system labels don't matter. It's just upwards, all right? So when you plug all that in here, that's what I was just saying. It's like, oh my gosh. Oh, whoops, I guess I just, well, whoops, I slid down too far there. But we didn't actually work out the limits yet. So this is, you got to go all the way around a circle. Because we're doing calculus, we can't use 0 to 360 degrees. Calculus and degrees don't mix, so we got to use radians, so it's 0 to 2 pi. Okay, again, 0 to 2 pi. And so when you get all this stuff, that's great. And this is such a common answer. Where is that? Right here. It's right there on your equation sheet. Now notice I didn't give the units, but the idea is we can use that to build up other shapes in a few minutes. So this is where it gets cool. The big picture is, okay, if you want to build a rod, you pick something. The rod is a one-dimensional object. We're going to build it out of zero-dimensional objects. Points are zero-dimensional. So when we want to build up a rod, we take the object that is one dimension smaller and build it. Now, if you wanted to build an arc, that's a one-dimensional object. It's got a length. Now, it looks 2D, but right, really, it's just you could define that by one parameter going around it. It's got 1 degree of freedom, which angle you're at. So again, we take that rod or arc that is a one-dimensional object, so to speak. It has 1 degree of freedom, and then we will integrate over a 0 degree object. So now if I want to build a disk, that's a 2D object, I need to build it out of rings, which have 1 dimension, so to speak. And if I wanted to build a solid cylinder, I would build that out of disks, which are 2D. And so we're always going to be building an object out of objects of 1 less dimension. Anyways, that's kind of the big picture, which is kind of fun. And I'll explain more about the units. You may be thinking this does not make sense because of the units, but it works out. And actually, you can see how we did it here, right? DQ. We end up just giving this, we take an object, which is essentially 0D, and we give it a tiny amount of length so that it actually has units of meters. And then the units work out. I don't know. Let's see. Oops. Yes, that's right, Trey. All you got left is that d theta. And so other questions before we just go flying past? Seems like you might be doing all right. And again, you could work ahead and work at your own pace, and you can watch this again on the YouTube channel if you want. All right. go back into here. And this is kind of what I was just alluding to. So we're gonna come back to this. I want to do one more example of an arc before we do this one. But so later on we can come back to this building discs or washers. So maybe what we should do is before we get past a ring, let's see if you actually know what you're doing with an arc. And so you could see this one, and this gets very tricky. Okay, and I discovered this problem. I basically found a problem in a textbook that looked similar to this, and then I made my own version of it. And in that book, they've put the angle right there too. And what I discovered is students had all kinds of trouble if the angle is not in the standard position. Okay, so again, I'm looking at this thing here, and I want to give you some hints as to how you could deal with this. Okay, let's say I give you a quiz question where it's not in the standard place. One thing you could do is read the next page. Another thing you could do is, can't you just do this? Turn it sideways and figure it out, and then unturn it sideways afterwards? Right, so imagine you're doing, right? You know that this thing is going to cause an electric field pointing straight down. Well, can't you just figure out this problem, which is normal, and then say, okay, we're going to go this way, and then afterwards just rotate it 90 degrees? You can. Yes, you can. All right. And so now I do think that when the problems become non-uniform like this, it's maybe worth it to read the next page. So I'm going to show you that in just a second. Okay. Whoops. All right. And let me get this a little bit smaller here. Oh my gosh. Come on. All right, and so again, we're going to try and do one of these problems in a minute, but just so you don't get lost, I want to show you the help file here, basically. Tips for understanding the R vector. And remember, we're going from the source to the point of integration for arcs. For some reason, students really suck at this. And what I've learned is this is what you can do. You can do the problem, and then you see these comments that I've added in here. Before you do any integration, make sure you didn't screw up the R vector by trying some different cases in different quadrants. Okay. And so, yeah, so yeah, you definitely want to know this stuff, right? All right. So again, rods and arcs, and I can't remember what I put on your next quiz, to be honest. I've written so many quizzes. I think I've written about 50 right now. Something like that. So I'm starting to lose my mind trying to keep up with all these quiz numbers and questions. But yeah, let me give you an example here. Look at this problem. So here it is. Notice the difference, and I want to try and emphasize this. This is an R vector, and this is a different R vector up here. So I want to point out the subtle differences. Now, normally in a math class, this is the R vector you think of. You think of radius times cosine theta in the positive I hat. Normally you think that, plus r sine theta in the j hat, because that's going radially outwards. This is the standard math. So in math class, you do this, right? Now think, in these problems, we're actually going from the source, which is out here, towards the center. That's why we get these minus signs right here. Okay, that's the source of the minus signs. And I'm going to clear that out. Furthermore, look at this. Sine and cosine get switched. Well, that's because I chose an angle to the vertical. All right. And so I'm not trying to screw with you. I literally just thought this was a straightforward problem, and it turns out a lot of people got messed up by this. So I wrote this. And again, the trick when you're doing this is write the R vector how you think it should be. Then before doing anything, make sure it works for some common angles, like something between 0 and 90 or 0 and negative 90 or etc. Okay. And let me clear that out. And I'm going to pause for a sec here and see. All right. Let me see. What do you think? So far, so good? Is this making any sense at all? Just maybe give me some feedback, no matter what it is, good or bad. I don't care.
It's making sense.
Okay. Obviously, we still need to practice it, right? So, all right. Okay. All right. Appreciate it. So let's go ahead and go back to that problem and try and do it. So again, you have the workbook. You know where it is. Let me do one thing really quick here. What is this one? This is something else. I think, let's see, did I make this the new version? Oh, I don't know where the new version is, but there's the workbook. If you, that's the old version. I think I put the new version in the, oh, it was in Canvas, wasn't it? That's the that link was. Let me see if I can. All right, whatever. Let's worry about that later. Okay, so Anna, if you're looking for the latest version of the workbook, it's somewhere. I don't know, but you can use this one in the meantime. Okay. All right. All right. So there's that. Let me get back to my. Okay. There's another example. Oh yeah, you can see a third example. So sometimes you even do get positives in there. So watch out. So you could choose 22.23 or 22.24. I think I'm going to try and do, oh, let's just start with 22.23. Let's not get too crazy here. Okay. So I'm going to draw it up and then I'll share the whiteboard instead of the screen. What's that question? Was that a question for me or was that just somebody?
I don't think so.
Okay, got it. All right. All right, so let me do this. There's a lot in this one that's good stuff. I know the black's kind of faint, so I'm going to try to use the black for my coordinate system. That way it's not too in your face. Okay, and I didn't explicitly state this, but the quarter circle, I'm going to assume that's centered. Did I say that? All right, so I'm going to assume it's centered. It looks centered to me. All right. Here's my random chunk. Here's my R vector. And I was told that this angle inside here is theta. So now I'm just going to check. I know it's to the vertical. So that's going to switch the sine and the cosine. And I'm just going to check. This side and this side. This looks like, again, this magnitude over here is capital R. So that's the magnitude. This is the vector. You're going to get a lot of these problems where there's a capital and a lowercase. So you got to get used to this, whether you like it or not. So this side is going to be R. It's adjacent cosine, and it's downwards. And this one is going to be R sine theta, and it's leftwards. That's where those come from. And again, I could check. What if I have a negative angle? Think. If I get a negative angle, sine of a negative angle is negative. So if I'm over here, the angle would be negative. It would be plus I hat because I'd get a negative. Now, what about the cosine? Cosine of a negative angle is positive, so I'd still get negative j hat. This is going to work for both positive and negative angles. So this angle up, oh, geez, I forgot to, I'm talking to the, oh my gosh, sorry about that, people. Forgot to stop the screen share. I really apologize there. Let me do speaker view. There we go. Sorry about that. Again, so I'm saying, let me go through that again. This is 0 degrees. I know that this is theta. Opposite would be r sine theta, and adjacent would be r cosine. So in this case, we see that the cosine is in the negative j hat. The sine is in the negative I hat. Got it. And like I was saying, if this is 0 degrees, these would be positive angles. And these would be negative angles. Sorry, this marker, I'm trying to squeeze the last little bit out of it. So, and look, if you have a negative angle, this is still going to work, because if you put in negative 10 degrees, this would be a negative number. I'd get a positive I hat. And this would be a positive number, so I still get a negative j hat. That's what I'm saying about write it down, think it through, check a couple of cases. Now, this is getting really busy. I got to erase some stuff. Again, you got the live stream if you need it. So getting back to our real problem, this is basically, that was all just, I don't like to do an integral before I'm sure it's going to work, right? That's a lot of work to do an integral. So there we go. That's my situation. All right, great. Now what about dq? What are the steps for dq? It's always lambda ds for an arc, which again, that's always r d theta for an arc. All right. At this point, what's lambda? I'll let you think. What the heck is lambda? I got to read the question again. So I'm going to read it carefully. If you haven't ordered that workbook, get it soon. It was totally the bookstore. They just decided not to order it. Don't you love it? Okay, there we go. Whoops. Oh, we're doing, what problem are we doing? Geez, 22.23. I should put that on the whiteboard. So it's uniformly charged Q. Got it. Quarter circle. Sorry, I forgot to number it. 22.23. So it's total charge Q. And it's a quarter circle. So what's the distance? What's the length? Maybe somebody that hasn't spoken up on Zoom. If you're feeling frisky, try it out. It's not a full circle. It's a quarter circle.
2 pi r over 4. So
Yep.
just pi over 2.
Awesome.
Pi r over 4 over 2.
Yep. So I'm just going to write what you said because that makes sense to me better. That's what he said, I think, to start. And to me, that makes the most sense. And then from there, you can obviously do, right? It's not all of 2 pi r. It's 1/4 of it, which then he was doing the math in his head. And it turns out to be that. But again, this is, where did he get this from? It was Q over 1/4 of 2 pi r. Make sure I didn't flip something upside down, right? You get a pi over 2, the 2 goes to the top. I think you get this. So far, so good? All right. Now, so we've got our r vector, we've got our lambda, so we've got our dq. We're ready to write this shit down. I mean, stuff down. Sometimes Zoom, it's very interesting. Sometimes Zoom will change the word ship into a swear word. I don't know why. Anyways, yeah. Okay, so in this case, which one of these terms is not going to matter to us? Remember, what are we trying to do? We're trying to get the electric field down here. This is a positive charge, use symmetry, and I think the I hat term will drop out and we should get negative J hat in the end. This is looking good. Nice job. All right, so I'm gonna remember that all I really need to do is this part. It's not that the other part you couldn't do, it's just we know that when you integrate, you're gonna have negative and positive limits. It's sine function, it's symmetric. sorry, it's anti-symmetric over symmetric limits, it's going to drop out. So I just forgot what I wrote down there. So I'm going to write this up here. Lambda was 2q over, what was it, pi r? And then I know I don't need that, but okay, I think I can have that memorized. So now the net electric field, you cannot do the magnitude. You have to do the whole vector. It's going to be k 2q over pi r. That's lambda times r d theta divided by what was the distance? Whoops, I'm going to run out of room here. I got to start over. I better go way over here because we got to get the vector in there, right? So this whole thing here is dq. Right? That's dq, k dq, and then the r vector was, now I'm going to cheat because I'm running out of room. We only need the minus r, I think it was cosine theta j hat. Now there was an I hat term, but by symmetry, we don't need it. And then what's the distance cubed? Well, the distance for every single point is going to be capital R, so then we got to cube it. So again, I did vector over distance cubed. And that's how you do that integral. And I'm going to check the chat and catch up. Okay, right on. Good stuff, everybody. Okay. Now, oh boy, there's starting to get to be a lot of R's here. So I'm going to try and cancel them out and not screw it up. Those cancel. One of these cancels. And now let's check a couple of things. We need to pull out the constants. K, 2, Q, pi. Capital R is a constant here. And maybe this is giving you an idea. While I don't always do this, usually little r is something that can change in a problem and capital R is something that doesn't. I'm not perfect, so I won't always do it that way, but most of the time you'll see in the notes and everything, I try to do that, okay? So capital R is a constant radius that factors out. So I think we get the R is going to pop out. The J hat is a constant. So we do have something left. There's d theta and a cosine, and all the rest pops out. So I'm going to try and write that down here. Oh, and the limits. We need the limits. So what's this angle right here? You probably recognize it as 45 degrees, which means this is also 45 degrees right there. But 45 degrees, yeah, exactly. We got to go pi over 4. And that's going to be positive pi over 4 from the vertical. And this would be negative pi over 4. Nice job. And that's one of the things you got to watch out for. You got to remember, oh, crap, I got to do radians, blah, blah, blah. All right. So nice job.
For this one,
Could question.
yeah, I was originally thought it would be 3 pi over 4 for the left end.
And it's because I'm going from this one. So remember, there's lots of ways you could do it. Now, if you wanted to, you could use this coordinate system, but then you got to use a different R vector. So this is one way to do this problem. Another way to do this problem, like I said earlier, is why do this at all? Just lay it down on its side and then just do it like a normal problem. And then you could see, oh yeah, it goes from positive pi over 4 to negative. And that makes more sense.
In this instance, wouldn't that the right side be negative pi over 4 then? Or I know it wouldn't matter in the end.
So it flips like that. So yeah, exactly. Yeah. So I argue in this case, I defined this as 0 and that positive, and I used that information to define my R vector, and then I checked my R vector. So that's why I am using this as a positive angle, because I said that, defined this based on that, and so they match.
I got you.
If you had done it the other way, you could have done this, and this would have been, I don't know what it would be, but yeah, you could have done it the other way, but then you'd have to define this as a positive angle and that. And like I said, you could define this as 0, and then it would go from pi over 4 to 3 pi over 4, but the R vector would be negative R cosine theta I hat minus R sine theta J hat. And so it's like, oh my gosh, no matter what you do, And even that one is tricky because it's still got the minuses in it. So you still have to think. I've discovered no matter what, you actually have to think on these problems. God forbid. All right. So yeah, it's tricky. All right. And yeah, all right. Good stuff. Now I'm going to rearrange this. Oh, screw it. Let's go to the solution. That's the important steps, right? So now let's see if there's anything we forgot. And it seems like this is the way I'm doing it lately, where I try and draw the nasty stuff, the setup, and then go to the solution. I hope that's working for you. You can send me an email if you don't want to talk now, but yeah, hopefully this is at least giving you some kind of idea. Where were we? We were at
I have a random question about this one.
okay.
Kind of unnecessary, but for this particular case, could we technically do 2 times the integral of negative pi over, or of 0 to pi over 4?
Okay. That's your intuition, right?
Yeah.
Class, what do you think?
Absolutely.
So why can we do that? Let me stop my screen share. So
To make
yes,
it
you're
easier
right,
on our
Ryan.
life.
No, that's why you would do it.
Yeah.
Not
Yeah.
why can you do
Why
it.
can we?
So look.
Oh, because when we take the integral, it'll be negative, subtracting a negative.
Okay, yeah, I don't want you to say. I want you to get used to the real words here. All right. So
Okay.
symmetry. Okay, that's okay. So you guys your intuition is right. I want you to learn the correct words from a math standpoint. These are symmetric limits. This is a symmetric function because it's symmetric about the y-axis when you plot it, right? If you're a water buffalo, you're ready to go. Okay. So like we see that because this area and that's why you have symmetric limits here. So why isn't this area plus that area the same as the whole thing? It is. Now, what I was saying earlier about the sine function, and the reason I'm asking you to get the math right is because we use this all semester, people. So here's a sine function, right? Notice the sine function is anti-symmetric. Okay, so it's positive here and negative here. So again, if we had stuck that sine function in, I'd get positive area and negative area. So the wording that supports your intuition, you were correct, Ryan. And all of you said good things, which were correct. I want you to think of it this way. Symmetric limits, even function, do the 0 to thing and double it. Symmetric limits, anti-symmetric function, so an odd function, if you will. So you could, I guess that's another way to say it is symmetric limits, even function. This has an even, all terms of the Taylor series are even. So symmetric limits, even function, double the area. Symmetric limits, odd function, all terms in the Taylor series of sine are odd. You can have that area drop out. So, all right. I don't know if I addressed that correctly, but Ryan, are you good on that?
Yeah, totally. That was really helpful.
Yeah.
Thank you.
Think symmetric limits, even functions. You can do the 2 trick. And then the other ones go to 0. Nice job. Outstanding. That was right on point. And yeah, it's actually better to have a 0 limit when you can do it. So, all right. And so let me see if I said this crap down here. All right. So there we go. I think we kind of did all this. Oh, what did I say? Oh, from there, I bet you could figure it out. And I bet you can. So I guess I should actually add that solution in. I must have been in a hurry, right? Gee, big surprise. You write thousands of problems, you're in a hurry. So what was this, 22.23? Finish it out. So I tell you what I'm going to do. I think I almost always do this in class. Let's actually finish it just because I didn't finish it there, okay? So, all right. So now I'm just doing the math. I've already lost the equation. So it was E equals, let's see. So I think I got to bring it up just to see it. And you might be right. And again, if you're waiting on me, just do the next problem and see if you know how to set it up. It's more important at this point to figure if you could set up the problems because I know you could do math at home. All right. So in this case, I just got to write this down. 2KQ. And there's a negative J hat. Okay. I got it written down now. Okay. And so now this was the part that we were just talking about. Symmetric, even. That allows me to do this trick. 0 and double it. So now it looks a little funny, right? There was already a 2 there. So again, you could think of it like this if that makes you feel better. Right? But you're going to get a 4 somewhere. And so now, integral of cosine, well, I got to think. The derivative of sine is cosine. So that should be it, right? So I get sine theta evaluated at 0 and pi upon 4, which is going to be root 2 over 2 minus 0, or 0.7071. Yeah, so I got to go to my calculator. And hopefully I don't screw up. So I get a 4 divided by pi, and then times, what was it, 0.7071? And so I got 9, whoops, 0.9. Oh, I'm in scientific mode, sorry. 0.99 or 0.9003. I hope that's what you got. I'll double check. That's right. 2.82. Oh, I divided by the pi. Check that, Jay. You have your pi still in there. Why have another numerical factor if you don't need it? Got it? Yeah. And that looks like you'll get it about right because you had 2.8, 3.1. That should be about 0.9. Now, when you look at this, this goes to what Jay and I were just debating. We said the same thing. Why is this, for an engineer, probably the best way to do it? Because I can look at this junk right here and say the units are right without thinking too hard, right? It's really easy to see. I got K on top, coulombs on top, meters squared on bottom. The units are right. When I plug in those numbers, I know it's going to work out. I see that my negative J hat makes sense, right? Because in this case, we had an arc. We expect right here, it should be straight down. Now, you could even go a little bit farther than this. What about the number? Is that number about right? Think. I know that's not fun, especially when you're tired. Well, look at this crap. Most of the charge is pretty much straight up there, right? So all of that is going to push it straight down like it's KQ over R squared. But this stuff has a tiny little bit of the X component get canceled out. So you might be thinking, this doesn't seem too crazy. Seems kind of reasonable. And let me get to the chat question. I know, no one likes to think. Yeah, I know. But yeah, so because that's all we have. And obviously, you know, I wrote all these Canvas quiz questions over and over and over again. How are you going to spot them if they're wrong? Number one, write down your work while you're doing it or take a screenshot of the quiz while you're doing it. That way we can go back and double check afterwards. Okay, that's one thing you got to do. Number two, thinking also helps. So, right, yeah, so that's the way you can kind of be like, clearly Jorstad is wrong here. Let's go figure out the typo. Yeah. But I mean, in this case, I think I got it right. All right. What do you think? That's 5:28. Maybe before let's look at one more setup before we take a break, okay? It's always nice to have the second half of the class be shorter than the first. So, at least for me. Let me go back to this one. So now, you can see that this one has a lot of going furthers. The going furthers are ways that I just say, oh, let's think about how does it change. So these going furthers are pretty important. Do not skip over them, all right? But let's start with the basic problem, 22.24. And one thing I feel in my heart is that you cannot truly understand this problem unless you understand what the density means. And here is one where you cannot just rotate it willy-nilly without doing a lot of extra thought. So you may be saying, oh, I don't need to learn this stuff that he's telling me. That's true, but I think it's going to be hard for you to understand this stuff if you can't just deal with weird coordinate systems. I'm not going to be the last person that asks you to deal with a weird coordinate system, okay? So you got to get used to dealing with it. And that's what one of the things this class is, I guess, good at. I don't know. All right, let's think. And hopefully you could do this without looking at the solutions right away, okay? Get a feel for how the charge is distributed. Positive, negative, where is it most concentrated? Where is it weakest? And then we'll get the electric field at the origin. All right. So I'm going to go ahead and bring up the solution and see if it makes sense to you now. Oh, I got to write down that number really quick. What was it? Okay, sorry, I'm going to make a note to myself. Got it. Throw that in the book after class. Okay, so this is part A, thinking about the density function. And so you've got all these words, but I'm sitting right here so I could just tell you about it. Okay, so I'm going to zoom in just so we could talk about the picture better. All right, you could do this by reading, or you could just listen to me right now. We know that this is 0 degrees because that's what the problem is indicating by this angle. Okay. Now, sine of 0 is 0. So that's what tells me there's no charge right here at the center. Okay. Sine of 0 is 0. Furthermore, as I go this way, I have a positive angle. This is a positive theta. This is going to be a negative theta because that's how the problem chose to do it. Now, as theta gets bigger, sine gets bigger, we expect more charge. Good enough. And so this seems reasonable to me. There should be a very small amount of pluses here, more, and then a whole bunch out at the end. So that's what I tried to indicate there. All right. And I did a bunch of words there if you care. All right. And this relates to other odd functions, right? So another way I might mix this up on a quiz could be, instead of having sine theta or something, I could just use theta. And so then you'd have to integrate and remember that theta is in radians, but even functions would be all positive. Odd functions would be positive on the right and negative on the left in this case. Okay, and then from here, the problem is easy, right? It's the exact same problem. We get the exact same result as before, except this, right? The density is different. So now we have a different density here. Let me use the annotation button. The density, this equation is exactly the same as before. ds is exactly the same, but this is what's different. So instead of using q, what was it, 2q over pi r, now we use this stupid looking thing. Whatever. All right. And let me get Ryan's question here. What's up, Ryan?
Wouldn't our R vector also be different because the X and Y left and right wouldn't cancel out then?
Oh, I see what you're saying. The R vector doesn't change, but which terms drop out do change.
Yeah, oh yeah.
And so so he's absolutely right that we want to think carefully about the R vector. So let's make sure we do that. So look at this one. In this case, since Ryan was nice enough to speak up, I was going to say crazy enough, whichever you want to say. All right, Ryan, you're
Little bit of
stuck
both.
with it now. Which way is the electric field at the bottom? Tell me. And take a guess if you don't know. It's okay if you're wrong. And I'll give you a minute to think. And everybody should be thinking this too. Because if you could know the direction the electric field will point, that saves you some math.
I think he's gone.
I scared him away. Right on. Okay, so that's what I get for asking a question, right?
I'm
scare
sorry.
him
No.
That's all
Oh
right.
gosh, I knew
What
I was gonna
direction?
get crap for that.
No, that's fine.
The electric field on
At
particle of
this
interest
point, at
would
this point, yeah.
be more to the left. Oh, it'd be directly to the left, wouldn't it?
You're right. Let's do
Oh,
a
wow.
Take a look. Think about this one. This is my attempt to draw that. That's going to go this way, right?
Yeah, yeah.
Look for the partner charge. That's this one. This is a negative, so it's going to pull up. And because they're the same amount, because it's a symmetric density, the net effect is that way. And again, it's going to be this much plus this much, so it should actually be about that long. Sorry about that. All right, but yeah, let me undo a couple. Should be that long, doubled, because the x component, so that tells us something that we don't have to do. So one of the reasons I hammered away on the symmetry earlier was so that you would be able to do this part. Oops. Let me clear those. Good job. Nice job. If you want, you can give him a round of applause there for putting up with the harassment. That's great. So, oh, whoops, there it is right there. Okay, blah, blah, blah. Okay. And so if you want, you could do this one. And then this one, you're going to have to do the double angle trick, right? So maybe you remember that, maybe you don't from calc class. All right, so there's a couple of these tricks in there. All right, there's a bunch of words. Okay, great. So I want to go back to the question and see, and I guess I should be careful here. So Ryan, did we get your question right? Or did we address it?
Yeah, definitely. So in that case then of this, I should say uniformly non-uniform charged rod, it just
symmetrically non-uniform.
Symmetrically, yeah. It just changes which one cancels out because one actually ends up canceling out anyway.
Yes.
Interesting. Okay.
And so imagine I gave a Canvas quiz where some of you had an even power and some of you had an odd power. You'd have to oh crap, you got to think for yourself when you're doing it. And there's tricks that you can make these even. Yeah, let me just leave it at that. All right. So yeah.
You could cancel out too then, couldn't you? You could cancel out the J hat and half of the I hat, double it.
I think so. And let's double check. And did I oh, it looks like I didn't bother to finish this one either. I probably didn't have time. So I'll go ahead and do that one right now too. So and it looks like you're right. I did the doubling right there. Do you see it? Because in this case you have an even function, symmetric limits. It's okay to do the doubling. The other one was an odd function over symmetric limits, cancels out right there. And how do I know? An even function times an odd function is odd, right? So, which is a little different than math, right? An even number times an odd number is even. But functions, it's not the same, right? Think about x versus x squared, right? X is an odd function. X squared is an even function. X times x squared gives you x cubed, which is an odd. So if you want to remember it that way, that's how you could do that. All right, I better go ahead and do this one really quick. And then I'll write this answer in there too. So I'm just going to work it out. You work it out. We'll see if we meet at the end. Using that old double angle trick. let's see. So I think that's right. Okay, so now, well, I could do the 1/2 separately. So that's and I'll share my screen in just a second here. I think I got it up now. So again, all I'm doing is I just did this integral and I'm splitting it into pieces. So it's going to be this times the first minus this times the second, because there was a minus there. And let's see, I'm just going to try and do this one. So I know the derivative of sine is cosine, but I've got a 2 there. So let me check if this is right. 1/2 sine of 2 theta. And now I don't know if this is right. I'm going to check it. When I take the derivative, a 2 is going to pop out by the chain rule and drop that down. And I'll get derivative of sine is cosine. So this looks good. So now I'll put my limits on it. Always check. Now, in this case, the 0 limits drop for both of them. In general, that's not true. Okay. So do not just assume blindly that, oh, anytime the lower limit is 0, the function drops out. I have a tendency to screw you like that if you try to believe that. Okay. So I don't know how easy it's going to be to do that in Canvas, but I will try to keep you honest. Always check both limits. It doesn't take that much effort. Yeah, you don't want to lose points for something as stupid as forgetting to check the lower limit. All right. So, all right, let's go in here. But in this case, the 0 limit drops. In this case, sine of 0 is 0. Whew. If it was cosine, obviously it wouldn't drop. So that means I could just change this to, let's see, pi over 2. And this will become pi over 4, if I'm not mistaken. Again, all I did was I plugged in the 2 limits and there was a 1/2 in there. So now let's clean this crap up. The 1/2s drop. And then let's see, sine of pi over 2 is 1. And then this, it looks like, so I'm just going to write all this down. Ooh, and minus a negative becomes a positive. So it looks like K alpha over R. Let me see. Something seems funky here. We'll check it at the end and see if I screwed up. All right, so that's 2K alpha R in the I hat minus K alpha. Oh, I think this 2 canceled that 2, didn't it? So now I'm getting lost here. Pi over 4. Something like that. I feel like I missed a 1/2 somewhere. Man, I can't remember what this was.
Wouldn't it be cosine 2 pi over 2 because it was 1 minus cosine 2 pi over 2? So wouldn't the 2?
Ah, thank you. So this should have a 1/2, shouldn't it? Is that what you're saying,
Yeah.
Sam?
Yeah.
Nice. Biology power, people. So there's a 2, and now I feel good. Sam saves the day. Nice. All right. Remind me when you're a doctor, I'll go to you. You pay attention to details. I like that. All right. So that's good. So now the reason I was worried is what? Maybe you could tell why I was crapping my pants. If this 2 hadn't have been there, if this 2 was gone, is the field in the positive or negative I hat? This term is bigger than that term because 3 and 4, that's less than 1. I was like, oh shit, this is in that zoom with the ship. I don't know why it does that. All right, so here we go. Anyways, out of this, I think let's finish this out. K alpha over R times, it looks like the quantity, this is going to seem a little strange. I want to factor out the negative I hat because I know the answer should be in the negative I hat, right? From the picture, I know that it was going left, like what Ryan and I were talking about a minute ago. So now if I factor out the negative, this one becomes positive, pi over 4 minus a half. And now I'm going to punch that in because I don't want that number. A little glare there. Weird. I don't know why that glares. Whatever. So pi div 4 minus 0.5. 0.2854-ish. So that I'm going to write down too. Anybody else get that? If you did, you could just unmute and say yep or nope. That was 22.24. I can't believe I forgot to solve those. Negative. Let me just check it. Is anybody else getting that? Yeah, hopefully. All right. Is this making any sense? Let me ask that. Some, maybe. Okay, couple.
It is. I'm just getting stuck in like the integration weeds that I haven't been through in a while.
Understood.
But the concepts are making sense.
Got it. Got it. Yeah, and so that's the practice part, right? The speed. Yeah. Okay. Yeah. That's good. That's good. And so I can't remember which quiz it was. There's a couple coming up. There's this chapter and one of the next chapters. I think it's, what is this, 22, and then the next one where it happens is 24. And I can't remember which quiz it was, but I literally didn't ask you to do the whole integral, but I asked you to set it up and then pick the right setup out of 10 or 12 different integrals that I drew for you. So it's really important to focus on making sure you set it up correctly. And then the rest of the math, I think we all agree you could plug it into Mathematica or something. And, you know, if you're using Mathematica during the quiz to do your integral, that's not going to offend me either. So one of the quizzes, I think I even said, you better use Mathematica to save yourself some time. So if you want to get in the habit during this semester of using an online program, that's not going to offend me. That's using the tool, and that's just what we got to work with right now. So, oh, sorry, Mathematica. How about Wolfram Alpha? If I say it that way, does that make sense? No. Oh, maybe that was a joke and I just didn't get it. All right, my bad. I'll show you what I'm talking about here. Let me just give you one. Give me just a second. I think it's this one. So, and again, I can't remember which quiz it is, but there was one of them where you get a cubic equation, and you're not going to solve that by yourself. Has anybody ever solved a cubic by hand? If you have, something's wrong with you. All right, so you got to learn how to use this. Did I put that in the chat already? Yeah. So you can use that or figure out how to use a computer to help you. I don't mind you using technology that's available. Oh, does it? Okay, my bad. Let me just take off the calculators. Yeah, I think so. Yeah, so just take off the word calculators and that should get the job done. And so you can learn about how to use that before the quiz happens. So if we were doing this in class, I wouldn't allow you to do that because it's blah blah blah. But in ERT mode, we got to shift our thinking and just say, okay, if you have an integral, use it and use the technology. Just don't use your friends. right? That's the thing that's going to piss me off. So yeah, there's another one. Yeah, sure. And you can add any other ones that you want in the chat, or if you're not a member of that Discord group, you could one of you that knows what that is can throw that in the chat too, and you can add this to the chat somehow, and you can come up with your best strategies for success there. All right. I think this is a good time to take a break, and especially if we wait like about 10 more seconds, we'll come back at 555, which is my favorite. Thanks, Nate Dogg. All right, so let's go ahead and take a break, and I'll try and start back up at 555, and I'll pause. I don't know. I'll just keep the live stream rolling. That's less book work on my end, so I don't know, unless you guys care a lot. All right. Give my ears a break. All right. All right. So let's see. Where are we? Yeah. Okay. So let's see. Where are we at now? Oh my goodness. Oh yeah. So we're almost done with the with this chapter. So I want to show you. I know this is going to seem a little strange. Well, big surprise. It's coming from me. It's strange. So now, whoops, where do I go here? I don't want this. I don't want this. Where was I? I want this. No, I want this. All right. And so in this case, I want to skip ahead towards the end to the summary, which is somewhere here. So we kind of talked about this. By the way, this is a great problem right here. This will work you guys over. So it's, you may think you got it down. And so if you can't do 22.25, you don't know what you're doing. All right. And it's, you'll see. Let's just leave it at that. Okay. So that's why that one's there. And again, you may think I'm making that crap up. I found it in a similar textbook and modified it to be my own. All right, so I'm going to talk about this in just a second, and notice that it's not usually a focus, which means not on the quizzes or the final exam, but we'll come back to that. This is what I wanted to go over, the summary, okay? So let's kind of think about this big picture, and so I don't know what page that's on. Zoom is covering up something. 27, okay? So in this case, let's kind of walk through this together and make sure we have the big picture before we go on to the other stuff. And this is what we're going to go on to. So kind of follow this through. What do? We build up rods and arcs out of point charges. This is the formula you use, right? Because that's the formula for a point charge. If we're building it out of point charge, dE looks like the point charge formula. R is from the source, which is the charge, to the point of interest, where you want to get the electric field. dQ is lambda dx for a rod, or it's dQ is lambda rd theta for an arc or a ring. If it's uniform, it's always charge total over length total. If it's non-uniform, you get some formula. So far, so good. For an arc, the total length is R times theta, where theta has to be in radians, not degrees. Okay, and you can remember the roundest knight at King Arthur's table is circumference, right? R pi, whoops, okay, 2 pi R. So all the way around is 2 pi. Somehow that joke reminds me of this calculation. And so if that works for you, great. If not, oh well. And then again, we assume our rods are 1D objects, so your slice also has to be a 1D object. Look at this. dQ is the slice of charge. Okay, it's a one-dimensional. It has units of meters slice. Why? Okay, because it's a 1D object, 1D slice. A rod is a 1D object, right? And again, if I have a rod, right, there's basically one dimension that tells us how far along that rod we are, right? So there's X. That tells you everything you need to know about the rod. So it's a 1D. This is 1D. Good. Now, what are we going to go to next? We're going to build up thin discs out of rings. That's our next phase. Okay. You could use the ring formula. So instead of using point charges, you use rings. Now look carefully. We figured out the formula for a ring earlier. This looks slightly different. Okay, if I could, let me get that ring formula here. There it is. That's the ring formula. Now I want you to pay attention closely to what changes when I go back. And actually, I have it on the next page here, I think. The idea is this is how we need to modify it. It's going to be K. Instead of a big Q, it's a tiny amount of charge. And we want to make sure we're building this thing out of the ring radius, which, and so, yeah, I'm going to go back to the other, so you have it. That's what we're going to do here. So notice it's K, Z. We've got a DQ instead of a Q, and we've got a little r squared instead of a big R. For more on that in a minute. R is the radius of the ring, or the radius of your ring-shaped slice of a disc. Z is from the center. DQ is equal to this crap. Great. I'll go into that in the next problem. So notice this, though. It's an area. A disc is what we're building. We want to build, let me draw. The idea is we want to build up this two-dimensional shape. And so what do we have to do? We need to build it out of rings. And so, whoops, that's not quite centered there. Sorry about that. So the idea is we're going to build up this purple disc out of these rings. And so because the disc is 2D, the rings are going to have to be 2D somehow. Yes. And so, Jay, what you're going to see is I'm on the quiz questions in Canvas, I would do rods or arcs mainly. Now, your final exam, I could ask you about these to keep you honest. So that's where it might show up. And I do think it will help you get a better understanding of those other things. So basically, you got to do this in case I ask you about it on the final. And so now I know what to ask to see if you guys actually did what I said. All right. So anyways, enough of that. Let's go do a problem. All right. But just know this is a summary here. And generally, we got to watch out for this. You could do the vector, but you can't do the magnitude. In certain special cases, it will work, but not always. All right. So, all right. And if you want, you could go back and look at them and see which ones would have worked. All right. So let me go back to here. And whoops, back to here. Whoa, no. Where am I? Geez, this one? Sorry. That's rods. Okay, there we just did arcs. Sorry, I'm scrolling here. This is it. Now we're on page 23. Okay, so this is the detailed version of that. Okay. So now notice the symbol is different for density. This is one of the things you got to look out for. Lambda has units. That's what the square brackets mean. I want you guys to get good at this. Those of you that didn't have me for class before, you should know this. That means the units of lambda are coulombs per meter. That square bracket means the units of. The units of sigma, look at the equation right here. Look at this equation. dA is an area, so this is going to be in units of coulombs per meter squared. Okay. And I don't know how I lost somebody there. Where did it go? All right, I don't know. Okay, whatever. Somebody I think just tried to come in. Hopefully that worked. All right. In any event, so and it's the same crap as lambda. If it's uniform, figure it out yourself. It's going to be charge over area. Okay. So if uniform, if uni, sigma equals Q total over area total. Okay, so that's a good one. If it's not, it's some function. So if it's non-uniform, you get some function. All right, I'm getting too much junk on here, but let's take a look. So the idea is you get the total electric field by building things up out of rings. And I believe one of the SBCC lectures, he shows you how you could build a hemisphere of charge out of rings. And that was one of their test questions one semester. So if you think I'm the only one that does this, that's just not true. Okay, so notice here's the general field that we found. And now, how do I change that if I want to build something out of rings? I need to change the Q and I need to use my little radius. So that's why these letters changed from capital to lower cases. Okay, let's see if we could do the problem. Oh shoot, there's the button. It was covered up by my toolbar. Hey Alexis, sorry the Zoom was covering up the button to admit you for some reason. So that's my fault. I didn't know. I'm sorry about that. All right. Okay, sorry. I'm getting too much stuff here. Let's scroll down and do the problem. And I think, where is it? Okay, there it is. So let's try and do these two problems. So if you've already been working on it, great. If not, so we're going to try and see how this thing generalizes and deal with the units. And I think that makes you a stronger student with the stuff that I'm going to test you on. So here it is, 22.21. I'm going to draw it and then we'll do it on the board. I'm just catching up here. So we got a solid disk. It's not a very good looking disk. Okay, we're up some point here. Distance Z, the radius of this stupid thing is capital R. And I think it was uniform and total charge Q. All right, I think I got it. Okay, so now, whoops. And I think this was problem. Oh, I lost it already. Oh, shoot. 22.21. Okay. So we know what we're trying to do here. What I want to do is I want to take this giant solid disk, which is this is supposed to be a circle, and I want to build it up out of rings. So again, I want to build this thing up out of these little rings, and each one of these little blue rings is going to contribute to the total charge, and it's going to contribute to the total electric field. And you might notice by symmetry, if this thing is really sitting right on axis, the electric field is going to be upwards. Okay, so I know this is going to work out, and this is one of those rare problems where I think you could actually do the magnitude and it would actually work. But let's get in the habit of doing it right. Okay, so in this case, E total is equal to the integral of E dE for my rings that I build it. Okay, and now I'm going to get that equation out of the book and write it on here. It was K dQ Z in the K hat, I think, in this case, and then all over R squared plus Z squared to the 3/2. Now, something you might be worried about, do the units work? Look, you got a Z up top and you got R squared to the 3/2, which is equivalent to R cubed. So we have meters over meters cubed. I have K, I have coulombs on top, and all this junk here works out to meters squared on bottom. Units work. Okay. Now, what is little r? Is that the same thing as big R? No, 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 no. Little r is the radius of my cheesy little ring. So that's little r. And I'm going to zoom in just in case you can't see this, just for this starting spot. My apologies for being so far away, right? So let's just zoom in and make sure we got this. The rest of it is just kind of making sure we get the pieces right. Okay, so this is supposed to be little r. This is big R. Z is how far up you are. This is the point of interest. This is the POI. And again, we discovered in some problem 22.20 This is the formula. And now what we need to do is take that general formula from that problem and modify it. dq, that's the charge on the ring. Okay. Not a rig. It's the charge on a ring. Well, that's going to be the charge density in units of coulombs per meter squared, or sigma. That's a lowercase sigma. Okay, that's a little small. So that's a sigma. Just draw a circle and then straight line, times the area of the ring. Now think, I was just telling you all day a ring is a one-dimensional object, but we can actually get a thickness here. It's really thin. Whoops. This thickness would be dr. So that's how we're going to get a differential in here and something to integrate. Okay, so we do have a tiny little thickness here. This is going to work out. All right. So now what is sigma? Sigma is, if uniform, sigma equals Q total over area total. And I'll get out of the way, which in this case, I don't know why I'm getting so much glare. What is this? I don't know. What can I do? All right. This is the stuff administrators don't understand. Oh, geez, I don't know how to get rid of that glare. It's killing me. Well, the total area is Q, or sorry, the total charge is Q, and the total area is pi r squared in this case. Notice it's big R. You're going to hear me say this a lot, people. Those of you that had me in class before are groaning right now because you're all like, oh, big R, little r. Is so much is relying on this, getting the R's right. Okay, thanks, Anna. All right. So big R, little r. This case, it's the total area. That's why I used big R, not my ring radius. So this gives me, let's see what pieces we have left. I know, okay, sigma, but I don't know dA. I'm going to have to figure that out. Little r, okay, we figured out, I think basically all we have left to do this problem is figure out what dA is. Now, this is where you kind of got to be creative and imagine you have this. Let me see if I have something here. Okay, here's a ring, right? It's a rubber band, okay? And so you could imagine, right, if I could try and draw this one, the whole distance, this is, all right, let me just kind of hold it out here. All right, so this is supposed to be a circle, right? The whole distance around would be 2 pi r, right? The thickness of that ring is dr. So the thickness of that rubber band right there is dr. And again, if I just snip this and cut it, do I have my scissors? I don't have my scissors, but you could imagine if I snip this and just lay it flat, it would be a strip. And let me do this with my notes here. It's easier to show you with my notes. This is what I'm trying to get at. So here you could see, here's the ring that I'm trying to build this out of. That ring is going to cause this tiny contribution to the overall field. We're going to add them up later, but so notice the whole way around is 2 pi r. When you snip that rubber band and lay it flat, its thickness is dr and its length is 2 pi r. Okay. And so that's where I got the, let's see, where is that one? Right here. dA is 2 pi r dr. Why? Because it's 2 pi r long times the thickness, which is small, just like dx was small before. Now dr is the small piece. And then we're just going to turn the crank. And so I think at this point, we've got everything you need. So let's use this. So hopefully the whiteboard and this together are working for you. So where were we here? Okay, so I got dA, I got this, I got that. I think that's all the same. So now I figured out dq. I just did a little math there to clean it up. Okay, so there's dq. So that gives me this piece to plug in. And when I do all this, you get this ugly crap right here. Now, Remember, this is not the electric field. This is part of the electric field. It's one ring's contribution. Little r is not constant, okay? We're going to take this circle and we're going to build it up out of the black ring plus this green ring that I'm drawing right now, if you could see that, plus this other ring, right? There's going to be lots of different rings that we use. And so we see that little r is not constant. Little r is not constant anymore. Notice it's got a dr. That's what's changing. So this is what's a little bit different. In the previous problem, we had a ring and we used d theta and the radius was constant. In this problem, the radius is what's changing because we're building a disk out of many rings of different radii. The radius changes now, not the angle. All right. And so when you get to this, you get to this, how do you get E total? You add the contributions from each ring. You add up the little pieces. And when we do that, this is an integral that should be on, you could use Wolfram Alpha or whatever that other link was that somebody put in there. I don't care, right? Or just not, you just can't use your fellow students during a quiz. The other way is, I think all the common ones like this one, I think show up. And I personally am pretty fast with a table as long as because these ones you're going to see, if you want to, you've got the integral table here on the back of the book. And I think, wasn't that this one? I think it was. I'm going to check because I'm reading it backwards and it's weird. It's flipped for me. Let me check it. So I get an R over that. Yeah, I think it's going to be this one right here. So I just use the table. And so there you go. Now, okay, so you could use the table. If you don't like it, you could see how I did the math here, blah, 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 blah. And so at some point you get an answer somewhere. I have no idea. All right, whatever. That's just a bunch of math. You could do that at home because we're running a little bit low on time. And you could see there's something here that may seem very strange. Earlier in the semester, some student asked, oh, can't we just use epsilon naught? Absolutely. And you're going to see that this is one of the problems where we start to use this other constant, epsilon naught. So K and 1 over 4 pi epsilon naught are the same thing. And if you want, epsilon naught is just, I'll put it in the chat. So obviously the units are going to be flipped upside down from K, but it's that 8.85 10 to the negative 12th number. So if you've seen that on the internet or you're wondering what epsilon naught is, that's a very useful constant for the next chapter. So, and it turns out this result is very cool because it relates to the next chapter. And that's why I decided to go to epsilon naught land. The rest of that's just math. I think you could do that at home. You got it all. There's some weird math tricks in there, so make sure you go through this one. Let me pause and see if there's any questions. Am I losing you guys here, or is this? I have no idea. I'll get the gallery view so I can see you. Okay, right on. Okay. Yeah, so I'm trying not to go too fast while at the same time cover everything. All right. Just checking to make sure I cover everything. Oh yeah, okay. There's a couple of other things in here I wanted to say about that. Here's something cool. Let's go back to our picture of this thing. What if you had a really large piece of metal, like a giant cookie sheet, or a big metal disc? Anytime you're close to that metal disc, Z is much, much less than capital R. So here's another question for you. What if Z is much, much less than capital R? If you use a really big piece of metal and charge it up, or a really big piece of plastic, whatever, Or if you use a small piece and you're just extremely close to it, like a millimeter above a standard piece of paper, right, that's been charged. Z is much, much less than R. This is an infinitely large plate. Okay, so it's not really infinitely large, but it's almost infinitely large. Let's go, I don't think you want to cut Z out of the integral, but we could cut it out of the solution to the integral, Corey. So the idea with that is you don't want to do the cutting out of the integral. You want to do any of that stuff after you do the integral. Okay, so let's go look at the solution and see what happens. Yeah, generally speaking, it's dangerous to not put something in the integral and do the math. Oh, I've got this annotate mode. Okay. There we go. Now take a look. What do you get? No, this is what's weird, Nick. You would think, now remember, if Z is much, much greater than R, you would be right, Nick. If Z is much, much greater than R, that should reduce to KQQ over R squared, right? Yeah, so absolutely. So Nick just raised a good point. We have two extra ways to check this. What if Z is much, much greater than, or what if Z is much, much less than? Or Z is greater or much, much less than. So this is the other case. So Nick already told me what should be true here. The electric field should equal KQ upon Z squared in the K hat. So now look at this crazy looking equation. It doesn't look like that at all, but it actually will get you the right answer, because look, if you go back to this mode, you can see what happens here if Z is much, much greater. And you have to do some thinking here, and you may have to use L'Hopital's rule too or something. So yeah. All right, so now the other one that I want to do, if Z is much, much less than R, because that's a little bit easy, I hope you agree that this would be negligible, and you get Z over R, which is also negligible. And so you get just sigma over 2 epsilon naught. Sorry, let me color code this. If Z is much, much less than R, this second term drops out because this, and then you get this answer. In this problem, is sigma constant or not constant?
Constant.
Yeah, exactly. Sorry, it's always weird asking questions. In class, it's a lot easier. Zoom just sucks for, yeah, so thanks. I think that was Ryan, so thank you. So yeah, look at this. Epsilon naught is a constant. What? The electric field is constant for a really large plate. Now, this is a big deal. In the real world, it's too hard to deal with complicated electric fields. If you're trying to do an experiment, you want to set things up so they're easy to deal with. So you use a large metal plate to make a constant electric field. Now, in practice, it's much easier to take two large plates and attach a battery to them, and then you get a large uniform electric field in between. And so what happens is, in practice, if you take two large metal plates and put a battery on them, the electric field inside is constant, and this is going to be a really cool thing we can use if we were actually in lab. But yeah, in a practical thing, that's kind of cool. So I thought that was worth pointing out. All right, there's that. And the other one, you could go through the long, painful derivation to see what happens when you set the other way. And Nick, I think you brought that up, right? Is that you?
Yeah.
So do you know what you would do if you had to pick Z much, much greater than R? How would you?
What do you mean? What would I have?
Oh,
to do?
how? Okay, so if Z is much, much greater than R, what would you have to do to this? Do you know?
Oh, I wouldn't even go to that.
I like that
just,
answer.
I would just think about, if the distance is so much greater, then that means the little disc might as well just be a point charge because the,
Yep.
yeah.
Well, okay, that's good. So what I'm saying is, shouldn't it mathematically match up to KQQ or to KQ over Z squared?
Yes.
Now, take a look. If we did the same logic, shouldn't this term just drop out and we get Z over Z? Right? Because R would be smaller than Z.
Right.
And so then you'd think it would just be 0. It doesn't look right. Binomial expansion is the thing I was thinking of. If you do the binomial expansion on this, so if you just set R equal to 0, that's the first term in the binomial expansion. That doesn't get the right answer. If you do the second term in the binomial expansion, then you actually can see this works out. And I've done that some problem, I'm sure, but I really care about that. I think physics majors should really care about that. I think it's really fun, but let's
I'm a
leave it at
computer
that.
science major. I'm good.
Yep, exactly. What would you do? Just start putting in bigger and bigger numbers and make sure it looks good, right? And do a percent difference and show that it converges, which is what we'll do to next week in lab. All right, whatever. That's maybe I'm boring the Nikes out of you guys right there. Okay, so that was that. Let's do one last thing. I'm tired. You're tired. Let's go back to the workbook here. Okay, so what's going to be different? Think. Don't try and do the math. What's going to be different? Which pieces of the derivation are going to be different? And you can speak up or you can add it into the chat.
The
I agree with
integration.
Jay, the limits of integration.
Okay, the limits of integration. And then Thomas, can you unmute and tell us what you're saying?
Yeah, you could do the limits different, or you could just solve the disk like we have before, and then subtract a disk from the middle.
Yeah, you could do that too. You could actually do it exactly the same and just subtract off the middle disk. But there's something else that's really important that's very different from before. If we were going to do the integral the same way, there's something huge. It's not just the limits.
The charge concentration.
Yeah.
Yep. Q over A total. A total is now 3 pi r squared, right? Pi times 2r quantity squared minus, yeah. Let's go look at it. So you got to watch out on these. Imagine if I all gave you disks and give everybody different inner and outer radii or something, right? Then you'd be like, oh, my charge density is different than so-and-so's, and you got to actually do some work. Okay, so just go into that next question. Change the limits and the charge density. And you can see the thing that most people forget, the one that I put in bold. So after you do that, you can go nuts on this one. All right. And so that really is this chapter. Oh, wait, let's go back. Let's make sure we get everything. Okay, so that's this one. We did the arcs, did the arcs. And then this stuff, again, I would not do these problems. Ryan, I'll be right with you. I would not do these problems, but look what I said. Just try to set them up to see if you actually understand what you're doing. And I promise I'm not going to put these on the final. So if you run out of time, this is the thing to skip, okay? So I'm not going to put these problems on the final when I ask you questions about them. The discs and washers, I might. But in this case, I think it's worth just trying to set them up and not do the integral, okay? So see if you could do that. See if you could follow these instructions. And notice now you're going to use rho, which is coulombs per meter cubed. Ryan, what's up?
I must be pretty tired. Could you explain to me again the charge density thing that you just went over?
Yep.
Just like maybe in like third grade speak or something. I don't know.
No, yeah, I'm going faster and faster because I see the clock running out. Sorry about that.
Is
No,
it
you're good.
because
You're good.
Is it because it's divided by area and the area is different?
Yeah, take a look. Is that good? I'll pause. It's the
I think so. Yeah,
it's
just
the
your value for sigma just changes. Okay.
Yeah, exactly. Because you have to use pi outer radius squared minus pi inner radius squared. One of those things. Now, I think somebody, who was it? Was that, who said that? Was it Taylor? Was that you that was talking about just do the 2 discs and subtract them, right?
Yeah.
Here's that way if you want it too. But look how nasty. I'm just going to warn you. Watch out, dude. So remember that you have to use the right charge density for your 2 discs. So you don't have the same amount of charge on them. So it's like, it's actually a lot easier to just do the integral. But if you want to deal with it, I showed you that. And look at, oh man, when I start doing sigma star and negative sigma, oh man. Yeah, you got to use the density here and use that to figure out the charges. It's just like, what a nightmare, right? So, but you were absolutely right. It just turns out in practice, it's probably easier just to change the limits, change the charge density, and turn the crank again. Is that good on that one? I forget who that was. Is that you, Tommy? Do you care if I call you
Yeah.
Tommy?
That's fine with me, man.
All right. How about T Biscuit? What's up, T Biscuit? All right. So Thomas, that was good stuff. All right.
Yeah, thank you.
Yeah. And so if you want to see how that's done, that's how it's done. All right. There was something else. Gosh, I'm starting to lose it. I'll just keep talking to myself and pretend I didn't know my Zoom mic was on. All right. There's some good stuff at the end of this chapter with the balloon. We already did that. We talked about the charge. Okay, so that's good. That's good. Setup only. What was it? There was something else. I know what it was. Okay, so I'm going to show you a little treat. If you guys think you know what you're doing, I got one for you. Okay. And just, all right, here we go. I remembered it now. So let me get this out of here. Now, I'm just going to show you. You guys probably know where all my old exams are, but if you don't, I'll show you. And I know it's a little bit weird. So I've linked these later on. Later on in the semester, about every 4 chapters, I put some links to exams in here. So let's start at the beginning. Here's Rob Jorstad, whatever. And then here's Physics 163. Here's my old exams, okay? And like, yeah, you can see the old exams and solutions. And so what I want you to do is at some point every 4 weeks, you got to do at least one of these, probably 2. Those of you, if you haven't been in my class before, a lot of students say like, gosh, well, the first one I did terrible. The second one I did terrible. The third one I did okay. And if you do 4 of them, you usually get an A on the final. So it's really hard to practice them all over Thanksgiving break. So you got to do a couple along the way. And so every 4 chapters, this is your study guide and all this stuff. And if somebody wants to, you could stick that in the chat if you want, or just whatever. But it's in your Canvas module somewhere. At approximately the right time, there's a link in your Canvas that says, do one of these practice tests. That said, I want to see if this is the one. You could see some old questions to practice. Where was that one? Oh, okay. So that was one I did one year. And you could see some ways that I varied that one. That's actually almost the same. I just rotated it. Where was that one? I used to be tough. Oh, there's the slab. I remember thinking this problem. So back in the day, I'm like, oh, this should be pretty easy for students. I guess it wasn't. Yeah, this was not easy for people. So this is, I'll put this link in there. If you want to do this, it looks like problem 3A. So if you think you can do this problem, and this will work you over. And like I said, the solutions are all there. I think it's fun, but I'm crazy. All right. So where is that Zoom? Where's Zoom? Oh, escape, stop share. And that's it for today. So if you want to get out of here, or if you want to do questions, that's fine. So that's a fun one. It was question 3. That's gnarly. So yeah, it could be worse, right? You could be getting that question and getting a 0. Yep. You know what's cool about this is we're going to do this in Python next week in lab. So, well, maybe that's cool. Maybe not. Yeah, I think it'll be kind of fun and lock this in. All right.
I have a question regarding the lab quiz.
Okay.
If you're okay going over that at some point.
Yeah, let me catch up on the chat. So Ramiro, oh, there you are. So lab quiz 2 is due next Tuesday. This Thursday, I actually let you retake the quiz that sucked the other day. And so Ramiro, does that answer that question? Oh, I could let me stop the live stream too.